The presentation of today, I will talk about statistical model for phase change, so mainly evaporation and condensation of droplet or ice crystal sublimation in atmospheric turbulent clouds. Okay, just an overview. I will go briefly on who I am and what I do, since Henrik already described quite well my past positions. Then some general motivations about the talk. A brief recap on the current numerical framework to study complex atmospheric multiphase flow phenomena. And then I will talk about what I did in the past about warm clouds, so it means mainly tropical clouds without the presence of ice, and some first results that now I'm investigating about the mixed phase cloud, meaning in presence also of ice. If there is time, I will talk a little bit about what happens at the cloud edge, a very special region on the cloud that separates the center wet region with the external dry region, and finally some concluding remark. Okay, so as Henrik said, I did my PhD in Rome. I finished in 2011, and then since then I moved to Sweden, North Europe, and I did my postdoc, my first at KTH, mechanical engineering. Then I did my second postdoc at Stockholm University at the Department of Meteorology, and essentially there is where I start this kind of research at the interface between fluid mechanics and atmospheric physics. And then since 2016, I'm at Chalmers University. So what I do, I study different kind of multiphase flows, especially the last years with a strong environmental application, usually suspension of bubbles in liquid water or microplastic transport in the ocean. I do also some more applied CFD simulation about urban cities, like in order to study the urban heat island effect, and also more industrial application like water absorption in porous media. Today I will talk about atmospheric cloud. So why they are interesting under a fluid mechanics point of view or multiphase flow? Because they are a very complicated multiphase system. So we have inside a cloud, usually we have a system of three phases. So water vapor, liquid, and solid. Solid if there are ice crystals, and there is turbulence around that mix all the three phases and interact with them. Clouds are very important for our planet radiative balance, so they regulate the amount of solar radiation that go towards the Earth's surface or go out, is reflected from the rain surface. They are also important for rain formation, and also they regulate water cycle in our planet. And so is very crucial. We will see soon that clouds are very crucial and important to have a very accurate weather or climate prediction. So, since clouds are very important for climate prediction, we always can wonder if we can predict weather and climate using mathematical models. So the first attempt was done at the beginning of the last century by Richardson. So is the same scientist that in turbulence has done Richardson cascade, or the dispersion of a pair of particles. And he had this idea to use a simple one-dimensional equation of motion for trying to predict the pressure in a location where currently that day he was doing his military duties in France. And so he knew the initial condition, let's say at 7 o'clock in the morning, and then he wanted to predict the weather like 6 hours later. So he did hand calculation, and unfortunately there was a huge mistake in the final calculation. So he was predicting 145 hectopascal of rising pressure, but the real data showed him that was essentially no increase in pressure the same day. Later, it was discovered that when he was doing the hand calculation, it was not aware of some numerical regularization that were discovered afterward in order to regularize the stability of the equation of motion. So let's say that for that year when he did this prediction were already state of the art. Some years later, the idea of how in the future weather prediction can be done by numerical process, by numerical simulation, this time a Joule 3D equation of motion, and that it can be considered a first step in computational fluid mechanics. As you see in this representation, this was the Richardson idea. We have the at the wall of a spherical room. You can also appreciate that there is a numerical mesh at the wall where a meridian and parallel intersect. And then there is a pointer where at direction the calculation around this point, a bunch of people doing and calculation. I mean, clearly it was impossible to have this idea in practice at that time, but then it will be essentially what we do nowadays with modern computers, that having a lot of people doing hand calculation, now we have supercomputers. So now, which is the state of climate prediction more than 1 century after Richardson's first attempt? So now climate scientists can furnish us climate prediction using numerical simulation. Here we see one prediction done by IPCC, the Intergovernmental Panel for Climate Change, that essentially for 4 different scenarios of CO2 release, they predict the temperature increase, the average temperature increase on the Earth. So we see that each line is a solid line that is the mean, but then there are a lot of uncertainty that are the shaded color area of the plot. And usually its uncertainty are attributed to the modeling or the not accuracy of model to represent clouds in climate model. You can say that here there is plus minus a degree of uncertainty. It can seem that is a small number, but in reality have a very huge economical impact and implication. So if we are ready to reduce of 1 degree, then we need to take some economic measure like electrification and clean energy and so on and so forth. So clouds are really a problem in models of climate prediction. Why is this the case? Because the composition of the cloud, in particular the number and the size of both liquid droplet or ice crystal, determine the reflectivity of solar radiation. So, for example, the climate model using the total liquid water inside a cloud as a model But if we look careful at the single cloud, the same amount of a liquid water can be distributed in fewer or larger drops, or in smaller and more numerous droplets. But you agree with me that in the case of a smaller drop and more numerous, the total surface of the droplet here is larger than the one on the left, on the cloud on the left. So it means that the cloud on the right reflect more solar radiation, and so will cool the Earth's surface a difference of differently from the cloud on the left. So it's very important to estimate the right droplet size distribution or ice size distribution inside the cloud, because it's what the climate scientists need to improve their model. And I will focus in the rest of the talk, on how to try to predict this kind of distribution. What is the current numerical framework in order to study all the phenomena that occur in an atmospheric clouds? So on the left part, scales of nanometers, we have the single molecule of both aerosol or water vapor that occur in the atmosphere, and usually here they are studied using, at least from a numerical point of view, from molecular dynamics. Then, as the scale of a single droplet or single ice crystal or few droplet, we can use a fully resolved direct numerical simulation. In between, we can have a mesoscale technique bridging molecular dynamics with fluid dynamics that is called fluctuating hydrodynamics. If we want to include the turbulent mixing or turbulence in general, nowadays the most appropriate way is Eulerian Lagrangian direct numerical simulation. And then at the scale of a full clouds, the current technique is large eddy simulation. And finally, scale of kilometers, we have simulation tool for weather prediction or climate predictions. So as you can see, there is not a single technique for standard computational limitation that bridge all these scales. So we need to model, whatever technique we use, model is unavoidable. So with all these huge scale separation, we need to improve the current subgrid model that each technique use from another. So I will start to talk about warm clouds. So warm clouds usually are tropical clouds. They are just composed by liquid droplet and water vapor. The temperature is clearly up 0 degrees, so no ice or freezing is present in the atmosphere. And we can have the structure of a single cloud that, from a fluid dynamic point of view, we have the central part of the cloud, that the bulk region, that we can assume safely homogeneous and isotropic clouds. And then we have the cloud edge that can be assumed as a turbulent mixing layer. So we have a turbulent region and a laminar region outside. And usually also the cloud region is humid while the air region is dry. So inside a single, all the clouds are very rich about fluid dynamic phenomena. We have also some interfacial stability on the top of the cloud and some entrainment of aerosol to nucleate new droplets at the base of the cloud, usually coming from salt that is available in the evaporation of ocean water. An important unsolved problem in warm cloud is rain formation. This problem is called also bottleneck bottleneck problem. And usually we still don't know how come that rain in tropical region appears in the first 20 minutes of cloud lifetime. So the process is quite relatively fast, and usually in order for rain to form, the droplet size should be very different, because if all the droplets are monodispersed, sharing the same velocity, they sediment with the same sinking speed, so they never collide. And so it means that larger particles that they can precipitate as rain cannot be formed. Instead, in order for rain, I mean big particle to form, the larger droplet should capture, that are fast, should capture the smaller one. Then there is coalescence, and larger and larger droplet can form. Turbulence has been indicated as one of the key mechanisms in order to explain the rapidity of formation of rain in warm cloud. Usually because of condensation, evaporation of the droplets, but also because they accelerate collisions between two neighborhood droplets that are not necessarily in the direction of the gravity. So I will focus here now in the condensation growth. So I assume the system is diluted, so the collision between particles due to turbulence can be neglected. A little bit of state of the art, like of history of the problem. Like 20 years ago, the domain of a typical DNS was like 10 centimeters, and we could carry 50,000 of Lagrangian droplet, but it was found that small-scale turbulence was not affecting the droplet size distribution, or the broadening of the size distribution. Then further simulation instead showed that if we start to increase the large scale of turbulence, so if we keep the dissipative scale the same but we increase the DNS domain, then we have more effects on condensation distribution. In particular, in this paper of 2009, they did some DNS simulation, and by increasing the Reynolds number of the simulation, so is, as I explained before, increasing the domain size, and then they stop after one eddy turnover time of turbulence, and they measure the droplet variance. So as we can see here, the droplet variance increase with Reynolds number, and the PDF, it seems that they reach the droplet distribution as steady state regime. However, if we take a look to this PDF, we see that the mean square radius here was 169, and the details of the distribution in the more turbulent case range from 168.9 and 169.07. So even so, essentially, if we put these plots in a larger scale, the effect is completely negligible. So what was happening then at that time? So we repeated essentially the same experiments, but for a larger domain and for longer simulation time. I will just go briefly about the governing equation of the system. So we have the standard Navier-Stokes equations. We are in the hypothesis to simulate the core of the cloud, so we assume homogeneous isotropic turbulence. We also evolved the water vapor concentration in form of a supersaturation field. So we have a transport equation of supersaturation, so convective term, diffusive term, a source term that is proportional to the vertical local velocity of the cloud. Usually this is called adiabatic cooling, because if the air parcel is moved upwards, then there is condensation is enhanced. And then we have a sink term, that is the phase relaxation is inversely proportional to a characteristic time scale. Essentially, this is when more droplets are in the vicinity of each other, they compete for water vapor. So there is this due to the release or absorption of water vapor, and it can be positive or negative depending on the sign of S. Usually, if the supersaturation is positive at the position of the droplet will grow, or if the supersaturation is negative, it will evaporate. For the Lagrangian droplet, we have a standard momentum equation, momentum balance for the droplet dynamics. Usually we assume Stokes drag with a nonlinear correction in the relaxation time, plus gravitational sinking. And then we have the equation grow for the radius of droplet. So the radius grows proportionally to the supersaturation, and is inversely proportionally on the radius itself. So meaning, like in all evaporation droplet, that the smaller is the droplet, more sensitive they are to the phase change. Okay, as I said, we did, compared to the previous direct numerical simulation, we did two things. We did a larger domain from 10 centimeter up to meters, like the simulation here with 2048 resolution is around 1 meter of domain. And we extended the computational time much larger than the editor-over time of turbulence, up to 20 minutes of, in the case of the smaller domain size. But clearly the one with the huge resolution will did like 30 seconds of simulation. Okay, what is plotted here is the standard deviation increase of the square droplet distribution. And we see one thing, that by increasing time, we don't reach a steady state, but the variance, the standard deviation always grow as t to the power 1/2, so as the square root of time. We confirm that we have proportionality of Reynolds lambda. So by increasing domain size, we have a larger variation in standard deviation, meaning that the larger scales of turbulence are responsible for the growth of the droplet. By manipulating the radius equation, we can see that the variance, so the square of the standard deviation, is proportional to this correlation, the correlation between the fluctuation of supersaturation and the fluctuation of the square radius. And we can see that if this kind of square root law is valid, then this correlation here must be constant in time. That is reached, we can see here in the direct numerical simulation. So after a transient, we see a quasi-steady state with variation along a constant value. Okay, how we can explain this result that we found in DNS? We derive a simple stochastic model for each droplet size. So we have one for the velocity seen by the droplet for the turbulent velocity. This is a standard stochastic model that in the Lagrangian formulation that was developed by research from Pop. So we have a relaxation to the mean that will be 0 in this case, plus stochastic term that is like Brownian motion, where Xi is a random number with zero mean and unit variance. We can do the same thing with the supersaturation equation. So we have the relaxation term here and the stochastic term at the end. We need to include the adiabatic cooling source term, the effect of the phase change. And finally, since S prime is correlated with V prime, we have another a stochastic term that take into account the correlation between vertical velocity and supersaturation. And finally, the equation of radius that this is deterministic, so we don't have a stochastic term. Okay, starting by this 1D stochastic model, it can be resolved very easily numerically. But at the time, for my surprise, we could do some analytical derivation. So after some manipulation, we can see here some moments of the distributions. And assuming now statistical steady state, we can solve these 4 equations by determining what we need. Okay, I skip again intermediate steps, but what we found is that the correlation I showed before between supersaturation fluctuation and square radius, we can see here that it depends essentially from the velocity RMS, from the eddy turnover time, and from the supersaturation relaxation time. It meaning that in this case, the standard deviation of R square increase for like the square root of t. So the standard deviation does not depend anymore on small scale. We can see that there is no dependency on turbulent kinetic energy dissipation, but just on the larger scale like the velocity RMS. So analogous, this is can be seen that the radius square, it behaves like a Brownian motion in the space of a radius square. Here we see some trajectory of the radius square extracted in time. We see the standard deviation here, the black curve, that it increases proportional to the square root of t. And there are droplets that are always growing and one that are always evaporating. So is turbulence act like a generation of radius square. So usually total water is conserved. It means that if some droplet will grow, some other need to decrease, but we never reach a steady state. Okay, if we compare now the model with the DNS results, the model now are the solid line and the symbol are DNS. We can see that the model always overestimate the DNS results. Here, for the smaller one, we have even order of magnitude difference between the model and the DNS. However, by increasing the scale separation, the difference between the model and the DNS results is reduced. Why is this the case? Because the smaller one, they have still effect of the viscous scales, so are not completely free from dissipative scales. But at least we have now a upper bound for the growth of variance. So we can be a little bit conservative, or at least have an idea how the droplet will evolve. So why not to do now large eddy simulations? Because in this case we capture larger and larger scales, and we are able to evolve a larger domain. So we see that in the case of large eddy simulation with a Reynolds number of 5,000, in this case the amount is quite good. And this is because now we have be able to capture larger and larger scale. So it means also that the Lagrangian model, the stochastic model, can also be used in to close the equation of motion for LEA's Lagrangian subgrid model for supersaturation. Later, our results were also confirmed using cloud chamber experiment at Michigan Tech University. So they use essentially a framework very similar to what we did. And also was at least the scaling as the square root also confirmed by other numerical simulations. Now, what happens if we also introduce ice into the system? So, in this case, now let's consider a three-phase system where are present ice crystal, liquid droplet, and water vapor. So let's see what change, how the dynamic change. First of all, some few preliminary thermodynamic concept about the dynamic of ice formation. So usually mixed phase clouds occur in temperature between 0 and minus 40 degrees. So we could expect that everything is frozen at this temperature, but instead some liquid droplet, they continue to stay in the liquid form. This phenomenon is called supercooling. So water is in a metastable system, so it does not spontaneously freeze, but remains, as I said, in the liquid state. That is a very dangerous process because it can affect airplane moving in this kind of clouds, because water solidify at the aerodynamic surface and it modify the aerodynamic performance. So a recent accident in Brazil last year was due to this kind of phenomena, because the de-icing system on the wing profile was broken. And it also affected the performance of wind turbines, especially in a country like Sweden or Nordic countries that where we can reach this extreme temperature. Another problem, so since water is supercooled, we have how ice is formed starting from supercooled droplet. Usually, in order for ice to be formed, we need special aerosol particles that are called ice nuclei. However, the number of these aerosols in the atmosphere is limited. That cannot be justified the amount of ice crystal that we find. So another problem is, another unknown question on this field is why we find so many ice in the atmosphere. One answer was due, again, considering some other fluid dynamic process of phase change. It's called super secondary ice formation. For example, here we have, if we have two different ice crystals, they can collide, for example, due to turbulence, and then break in different crystals. Or some other crystal can be activated in the wake of a sinking droplet, or other kind of, this is also interesting, is fragmentation during freezing. So if ice come into contact with a supercooled droplet, then first the external shell of the droplet start to freeze. Then, because of different density between solid and liquid water, the liquid water is compressed by the solid that has a smaller density, and so high pressure occurs until complete explosion of the droplets and formation of different fragments. And finally, for our purpose of considering condensation of water vapor, What regulate the amount of condensation is the so-called Wegener-Berger of in the same process that tell us that if we have water vapor molecules, they preferentially grow around or make grow ice at the expenses of the liquid water, and this because the supersaturation of ice is larger than the one of the liquid droplets, so that usually water vapor accumulate on ice, the environment become drier and drier, so it means that the liquid droplet need to compensate by evaporating, and the ice absorb everything until the liquid droplet completely evaporate. What we wonder now, considering the previous scenario, is how small-scale turbulence affect this process. So we did essentially the same equation of before that I show for the one cloud. The only different, so we have an equation for the mean supersaturation and for the fluctuating one, again with a stochastic one term, and the same for the square radius. Is a little bit complicated because there are kinetic effect here and also some aerosol curvature effect, but essentially is the same as the one of before. What we need to add is the link between the ice supersaturation and the water supersaturation, and essentially this is the physical mathematical description of the WBF process I showed before. So essentially this equation is telling that for given liquid water supersaturation, then the ice supersaturation will be larger just because they preferentially grow around the ice. We assume that the supersaturation statistic along water droplet and ice particle are the same, and that supersaturation statistics are Gaussian. We will see if there is time at the cloud age that there the statistics are not Gaussian at all, so this kind of model cannot be used in that case. We validated with the previous direct numerical simulation in this paper of Chen et al. And also with we are doing some intercomparison with different research group trying to simulate the again the cloud chamber experiment of Michigan Tech University. So for the A configuration, we have isotropic turbulence with Reynolds lambda 60, and for the second, 85. Let's start with the evolution of the bulk properties, the mean droplet radius and the mean ice radius. We can see that they are consistent with the thermodynamic scenario. So the mean droplet water it diminish in time until complete evaporation of the droplet. The same for ice, instead it grows indefinitely in time, especially for the case number 3. And here we have also the liquid water content and the ice water content, again diminish and increase. If we compare DNS, the solid line, with the stochastic model, the dashed line, we can see a very good agreement. But moreover, for the bulk properties, if we turn off completely turbulence, then we should see the dashed dotted line where just in few plots can be visible, otherwise they are superimposed to the dashed line. We obtain essentially the same result. It means that the small-scale turbulence does not affect at all the mean properties of the cloud. The same for the cloud chamber case. So we conclude the same thing. Stochastic model and DNS, they share a very good agreement, except here in one case, the green one, that is at the border between the complete glaciation of the cloud. So for this ice injection rate of 5, continuous injection of 5 aerosol per centimeter cubic per minute. In this case, we will see very huge difference between DNS stochastic model and stochastic model without turbulence. Why is that? We will explain soon. We can instead see that the turbulence instead affect the size distribution. This is the variance, the standard deviation normalized by the mean radius. We can see that the value are positive, meaning that the droplets or the ice are not monodispersed at all. We see here in the size distribution again that the stochastic model and the DNS, they share both the same distribution for ice and for water, again, except the huge difference we see for the green curve of these 5, that is the first cloud that will glaciate. So why this particular value? If we do some mathematical calculation, we can express the mean radius as a function of the mean quantity and about a Damkohler number of the droplets. We can see that when this Damkohler number is 0, essentially we have just the first term that does not depend at all about the turbulent fluctuation. But for larger value of Damkohler number, we can see that the Damkohler is multiplied by the variance of the supersaturation turbulent fluctuation. So in this case, it will matter more the effect of turbulence in the bulk properties. If we monitor here the standard deviation of droplet distribution with that, we see that indeed the larger value of standard deviation correspond to the larger value of the peak in Damkohler numbers. So about result on mixed phase clouds, so small scale turbulence weakly affect the bulk properties a small Damkohler number, but on the other hand, turbulence can have a stronger impact at a larger scale. In that case, the Damkohler number will be order of 15, or if we translate in length, will be around 20 meters. And so impacting the droplet size distribution. And this kind of model we develop can be used again as a subgrid model for the WBF process for meteorological climate prediction. If you want more details, you can find in our paper that we have recently managed to publish. Okay, I don't have, as I predicted, time to talk about the cloud age, but I just wanted to show you that in this case, supersaturation cannot be assumed as Gaussian. You see here a very high tails in the supersaturation profile. Then we need to use a different approach based on a mapping closure. Again, it was another technique developed by Pop for in the combustion field, and we applied for the cloud. I don't want to go into details, but usually the mapping closure model for Gaussian supersaturation fluctuation, it can be shown that coincide with what I showed you before. However, if we keep all the full dynamics, then we are able to see non-Gaussian distribution. Okay, so just let me conclude. I hope I show you that clouds are fascinating multi-phase flow system. There are a very complex systems, so there is turbulence, phase change, mixings, or other process that I had no time to talk, like aerosol chemistry interaction or electrostatic interaction between charged current that can appear in the particle if you think to storm and electrostatic formation. So modeling all these previous aspects is still an open field in the research, both in fluid mechanics but also atmospheric physics, and developing better model is crucial for more accurate weather and climate prediction. Finally, I want to remind that besides clouds physics, there are a broad range of applications where this kind of phase change can be important, for example, in climate science or iceberg dynamics in the ocean, or other industrial application as aviation, wind energy, beverage production, or anti-freezing and the icy system. And thanks a lot for listening, and I will gladly answer the one of you that have questions. Thanks.
Thank you very much, Gaetano. Very interesting presentation and very interesting work. There are quite a few questions posted in the chat, so let's see how. And I have some questions too. Maybe we will see how if we have time for all of them. I would like, the first question is, so you started talking about weather predictions, and yes, that is a classical application, let's say, within fluid mechanics that everyone knows about. So that is nice because you can talk to anyone about weather predictions. But the thing that people usually associate with weather prediction is that they are bad. It's difficult to predict the weather. So do you have, how do you explain to someone who does not know about the complexities of multi-phase flows that it is so difficult to predict the weather?
Yeah, I mean, I should say that in the last decades, at least, they improved a lot, thanks also to better modeling, but also better power, computer power. So I guess, I think I read, but I'm not sure, so don't let me grant that nowadays 3 days prediction, apart some rare events, should be quite accurate. But I mean, I'm not neither an expert, neither I can give you this as an answer. And yeah, I mean, probably the complication is because of this amount of scales. So usually the models that there are in weather prediction, or even more in climate prediction, they cannot represent all these phenomena. So they are very simplified, just sometimes just based on empirical correlations. And so that's probably the reason why still is a big challenge.
I see. So there are some questions about, let's say, the Reynolds number and the definition and its relation to the size of the computational system. So could you explain, so you have Reynolds number and how it relates to the size of your computational system in the DNS?
I just check the question. Okay, so wait, let's see if I recover my the original paper, because there is a table there. So what I show you is the Taylor-Reynolds number. Can you see the table?
Yes, we see the table.
Yeah, so essentially what I show you is the Taylor-Reynolds number, so based on the Taylor scale. And if we want to translate of the box, it range from 45, in my case, correspond to 8 centimeter simulation. And 600, the larger DNS, it corresponds even meters. I told 1 meter, instead it was 3 meters. And then for the large eddy simulation, then 5,000 correspond to 100 meters, but clearly here the small scales are not resolved. I hope I answered the question.
Yes, yes. So so that means, but okay. So what about what are the largest scales if you would want to resolve everything? How big box would you need?
Okay, so here the small scales, let's say, is always 1 millimeter, so the dissipation is the same. And so all these kind of simulation share the same Kolmogorov scale, but by increasing the length of the box, then you capture larger and larger scale. So the larger scale probably are, since it's periodic, is half of the box length. Yeah.
Yeah.
So in this case,
but in the actual cloud, how
no,
large are the?
then are much larger. Is more comparable with the large edge simulation.
Yeah. So how can one translate the information from the DNS to?
For this, then you need this kind of scaling law, because in that case, then I mean, you check that your model more or less predict, and you can quantify the difference, and then you can translate, or you can use a subgrid model for. So if you want to use the model as subgrid model, for example, if your LES, then it can solve up to 1 meter of resolution. So then down to 1 meter, you use the stochastic approach.
Yeah. And that is what you have shown, if I understand you, that the smaller scales are not important when it comes to the variance growth.
Yeah, but clearly if you instead consider also collision, then everything, collision instead on the other side are dominated by small scale turbulence, because just when particles are close. So if you want to consider the whole process, then it's more difficult to develop. You need a collision kernel that also, I mean, the model will be complicated. You need a better collision kernel if you want to include collision coalescence as well.
What about the Stokes numbers? What Stokes numbers do you have for the droplets?
There is so Stokes in the, I mean, the droplet are let's see if I find is
so even if you have the broadening of the size distribution, the Stokes number range is still, but they are small.
I would say below 0.1. Yeah.
Okay. Yeah.
So all this effect that, for example, clustering doesn't matter so much, because the Stokes is still small. And on the other hand, they are peculiar because the Stokes, even if the Stokes is small, instead the sinking velocity can be high, because of the large density difference. So you are in a system where you have a small Stokes number, but instead they sink quite fast.
Yeah. It was interesting to see. There was also a question about experimental verification, and I think you partly answered it because you showed those experiments in cloud chambers. So do you know, I guess, since talking about the scales of the actual clouds, that they are so big, I guess there's you must scale down the experiment. Is it difficult to achieve dynamic similarity in a cloud chamber, or how does it work?
Yeah, I mean, also for the experiments, it's difficult as well. Yeah, because usually you cannot match all the non-dimensional number, like Rayleigh number in this case, since there is buoyancy, and or the droplet. So the same thing happens also on the. I mean, one of the challenge about about atmospheric physics is also different, is because also laboratory experiments are complicated to do, because you cannot match everything. Yeah. But our model, I mean, if we compare with paper, for example, also the one of ice, where is this one, the cloud chamber, also the solidification, the glaciation of cloud also appear for an injection of aerosol between 5 and 10. So at least qualitatively also we match this kind of aspect. Yeah.
Okay, that is very interesting. Yes, maybe one final question. So when you do the mixed phase clouds and you have the ice particles, and there were some mechanisms, for example, you have this, you induce the freezing and you still have like a liquid core and maybe the droplet breaks and so on. Do you see that there's a need to do, I mean, now you're doing, let's say, point particle Lagrangian simulations if you want to see what the turbulence scales does with the particles, but if you have those internal processes, I guess internal circulation and so on could become important. Is that a future direction that you foresee?
Yeah, I mean, these, if I want to reproduce these, we are doing with fully finite code DNS, where we describe, so not with Lagrange, with volume of fluids, with phase change and supercooled equation of state for water. So we are working on that, but not with clearly with a Eulerian Lagrangian approach.
No, and then you need to somehow represent the forces that would tend to break the particle, I guess.
Yeah,
or you.
there will be a threshold on the fracture stress for the ice. Yeah.
I see. Okay, then we are at 2 p.m. Swedish time, 8 p.m. Chinese time, and we thank Gaetano once again very much for this excellent talk presentation. Thank you so much.
Thanks for the invitation again.
Thank you, and see you